And yeah, there is not so many participants today.
I hope more will come.
Yeah, I hope too. Okay, there I hear some Spanish background noise.
So I will mute myself.
Maybe people partied on Friday evening. Oh, there is Professor Giga.
Coming. Hi, Yoshi, how are you doing?
Fine. Fine. I'm sorry. I'm a little bit late.
You're on time.
Don't worry, you're on time. You're not late. Okay.
Good.
So I guess at this point maybe we can start. Okay, I will just allow Professor Tarcia and okay. So now as the first talk of the morning session, we will have Ken Shirakawa from Chiba University, and the talk will be about optimal control problems of grain boundary motions with temperature constraints. Please go ahead.
Okay, thank you for the introduction. First of all, I would like to thank the organizer, especially for Professor Piotr Rybka, for his kind invitation and for giving me a chance to talk this Zoom meeting. The title of my talk is Optimal Control Problems of Grain Boundary Motions with Temperature Constraints. This is based on the recent joint work with Professor Harville Antil, George Mason University, USA, and Shodai Kubota, Chiba University, Japan, and Professor Noriaki Yamazaki, Kanagawa University, Japan. Okay. In this talk, we consider an optimal control problem, a class of optimal control problems governed by the following state system. This state system is called system of Kobayashi-Warren-Kata type, and physical motivation is to describe the motion of grain boundary. In the Kobayashi-Warren-Kata type system, it is supposed that on a time interval 0 capital T, a spatial domain omega is occupied by a polycrystal. Here is a sample picture to explain such situation. This picture is a picture of micrograph provided by UBE Scientific Analysis Laboratory. In this picture, we can see that the area domain of omega is subdivided by several sub-areas. And in some sub-areas, we can see characteristic orientation by this stripe pattern. And other area, we cannot see such orientation. The former phase is called oriented phase, and the latter one is called disoriented phase. The free boundaries between these phases are called grain boundaries. In the system of Kobayashi-Warren-Kata type, the difference between oriented and disoriented phases are reproduced by using an order parameter denoted by eta. Eta. I have to switch. Eta. Eta. This eta is called orientation order. And on the other hand, the direction, crystalline direction, polycrystalline direction is denoted by another order parameter theta, and it is called orientation angle of grain. In particular, for the component of eta, we set some two threshold values. In our case, they are 1 and 0. And if the value of eta is greater than or equal to 1, then we read the physical situation is oriented. And on the other hand, if the value of eta is less than or equal to 0, then we read it is disoriented. Okay, the first equation is a governing equation for the component of eta, and it is described in form of standard heat equation with perturbation, with forcing term U, and in this equation we impose zero Neumann boundary condition and initial condition. The forcing term U in the optimal control problem, the forcing term U is set as a control for the component of eta. And physically, this U is supposed to be a temperature. So our optimal control problem can be said a temperature control problem of the optimization of grain boundary motion. On the other hand, the second equation is a governing equation for theta, and it is formulated with some quadrilinear parabolic equation with singularity. This equation, in this equation, we impose Dirichlet zero boundary condition and initial condition. And we denote by V the forcing of the second equation. This forcing B is called control for the orientation angle. Also, alpha naught is a given fixed Lipschitz continuous function. Also, alpha is a given convex function. And these alpha naught and alpha are called mobility. And it is supposed that these are involved in the control of grain boundary motion. Nu is a fixed positive constant, and eta naught and theta naught are fixed initial data. Now, based on these, we set our optimal control problem as follows. For simplicity, let us denote by Q, the product space of the time interval 0t and omega. Also, we denote by gamma, the boundary of omega, and we suppose it is smooth enough. Also, we denote by sigma, the product space of time interval and the boundary of gamma. Let H and calligraphic H be the basis space of our problem, and they are prescribed as Hilbert spaces L2 omega and L2 0th respectively. Under these notations, our optimal control problem is prescribed in form of a minimization problem for a cost functional with respect to the forcing pair U and V given as follows. In this context, U, the component U is a control for the solution, first component of solution of state system. And in short, it is called temperature control. V is a control for the orientation angle, theta. In this problem, eta and theta denotes the solution to the state system for any control pair U and V. Eta AD and theta AD is a fixed pair of functions which corresponds to the admissible target profile for the grain boundary. Moreover, in this model, we consider the problem by using constraint for the temperature control. And we denote by capital UAD the constraint class for the temperature controls. More precisely, we suppose that temperature control is always, the range of temperature constraint is always restricted between two obstacle functions, bounded obstacle functions denoted by sigma lower star and sigma upper star. This kind of constraint is often called box constraint for simplicity. Now, for the mathematical analysis of this optimal control problem, the singularity, as in the state system, brings some difficulty for the observation of Gato differential, Gato derivative of the cost. Cost is like this, and it is given by the sum of squares of L2 norms. So in one look, it looks convex, but this is a non-linear system, so the part of, associated with solutions does not show the convexity. Moreover, we have singularity in the state system, so it would be difficult to calculate the Gato differential of this cost. So before we start with our main discussion, we prepare approximating problem as follows. The difference between the original system and approximate ones is only 1 point, such that we replace the state system by regularized one. And in the regularized state system, we replace the singular flux in the diffusion of second equation by regular one by using a regular function defined as follows. More precisely, this regular function f epsilon is given in the form of a hyperbolic function parameterized by constant epsilon, and this epsilon approximates the Euclidean norm uniformly as epsilon tending to 0. So by using this regular function, the singular flux in the second equation is relaxed in a standard form. Now here is the content of the results. In this talk, we discuss about the following 4 main theorems. The first main theorem is concerned with the existence theorem for our optimal control problems. Here we note that since our state system is nonlinear, our cost functional cannot be convex. So in our optimal control problems, we cannot expect the uniqueness of optimal controls. The second main theorem is concerned with the continuous association between optimal control problems. However, since we cannot expect the uniqueness of optimal control problems, the statement of the second main theorem will be stated as some semi-continuous association, more precisely upper semi-continuity between the classes of optimal controls. The third main theorem 3 is concerned with a necessary condition for the optimality in the approximating optimal control problems. The main objective of this third main theorem is to characterize the Gato derivative of the cost by using linearized state system. And this main theorem 3 will be important as a base of the reasonable method to obtain an approximating optimal control. Finally, by taking the limit of approximating optimal controls, we obtain the final main theorem 4. This is concerned with the limit of necessary condition as epsilon tending to 0. This theorem corresponds to some partial result for the validity of the approximating approach as epsilon tending to 0. Now, here are assumptions required in our main theorems. The first, in this talk, we restrict spatial dimension between 2 and 4. And also we fix as a positive constant nu. That is a coefficient of the Laplacian in the second singular diffusion equation. And we fix 2 obstacle functions, sigma substar and sigma upper star. And we suppose that they are bounded and they are governed in this order. Next, for the mobility of alpha naught, alpha naught is supposed to be a fixed function, fixed Lipschitz function over Q, and we suppose alpha naught is positive. Also, for another mobility, alpha, we suppose alpha is C2 convex and alpha times derivative of alpha are both Lipschitz continuous on R. Also, we suppose that alpha prime, alpha takes a minimum at 0. And moreover, we suppose alpha and alpha naught never degenerate. Next, G, as in the first equation, G is a Lipschitz perturbation having non-negative potential, capital G. And we suppose there exists two constants denoted by rho substar and rho upper star, which satisfy the following inequality, marked green. Finally, for the pair of initial data, we suppose that they belong to the class of H1. And especially for the component of eta naught, we suppose the range of eta naught is always between two constants as in the previous assumption. Here we note that the parts marked red are for the uniqueness of the state systems. And let me mention that it is a different point from the previous studies by these mathematicians, including Salvador Moy, joint work with Salvador Moy. Also, we note that the conditions marked green are important to guarantee L infinity boundedness of solutions of state systems. The key point is the comparison principle for the second equation, first equation. Now, under these assumptions, we first show the following propositions. There are three propositions, and this is the first. The first proposition is concerned with the well-posedness of the state system. And more precisely, under these assumptions, we can show that the state system of Kobayashi-Warren-Kata type admits a unique solution defined as follows. The first, eta and theta. The component eta and theta satisfy the standard regularity of parabolic variational inequality. And next, the component eta satisfy the following evolution equation subject to zero Neumann boundary condition and initial condition. Next, the component of theta satisfies the following evolution equation formulated by using a set-valued function denoted by SGNN. Here, this SGNN is a signal function, multi-valued signal function on the Euclidean norm Rn. And this signal function coincides with the subdifferential of the Euclidean norm on Rn. Here we note that the singular part of the second singular flux in the second equation is expressed by using this set-valued function. And also we note that similar propositions hold for the approximating state system. And this is just a second proposition. And second proposition is almost the same with the first one. And the difference is only in the point that the singular flux in the first proposition is replaced by a regular one. And by using these two propositions, we can further show the following proposition 3 concerned with the continuous dependence of solutions. Hereafter, we denote by S sub naught the solution operator which maps any control pair UV, the solution to the state system of Kobayashi-Warren-Kata type. And as well as for any positive epsilon, we denote by S epsilon, the solution operator for the approximating state systems. Then for the class of these solution operators, we have the following continuous dependence with respect to the convergence of epsilon and weak convergence of controls, and the continuous dependence of solution is governed by the strong topology of the class of C0TH and L20TH1. Now, by using this proposition 3, we can prove the following two main theorems. The first main theorem 1 is concerned with the existence of optimal controls for the original problem and approximating ones. And the proof is this theorem is proved by using standard argument, minimization argument. And then we need to apply the continuous dependence of solution operators. The second main theorem is concerned with semi-continuous association between optimal control problems with respect to epsilon. More precisely, if we take the sequence of approximating optimal controls, then we can find a subsequence of epsilon, and we can find the limiting pair of limiting functions such that this sequence, the sequence of approximating optimal controls converges to this pair of U star V star in the weak topology of L2. And moreover, we can say that the weak limit is optimal control of the original optimal control problem. Okay, now next, let us look towards the necessary condition for the optimality of approximating optimal control problem. The key point will be the Gato derivative of the cost. And in our study, the Gato differential is characterized by using a linearized state system. And here is the auxiliary system for the necessary condition. And in this auxiliary system, we have 6 coefficients denoted by A, B, lambda, omega, capital A, and mu. And for 5 components except for mu, we suppose they are bounded on Q. And more especially for the component of A, we suppose that A is Lipschitz continuous on Q and A never degenerate. Moreover, for the component of capital A, we suppose that this capital A is positive and symmetric matrix valued function almost everywhere in Q. This capital A corresponds to the Hessian of the singular Hessian matrix of the relaxed singular diffusion flux. On the other hand, this mu, for this mu, we suppose mu is non-negative and mu belongs to L infinity 0th. So if the spatial dimension is less than or equal to 4, then we can apply Sobolev embedding theorem and we can prescribe the solution of this auxiliary system in the range of L to 0t H1 dual. This class is a suitable class to define weak solutions for the parabolic variation inequality. So this is a principal reason why we want to restrict the spatial dimension. This auxiliary system is a generalized form of the linearized state system. So for example, for the case of Gato derivative, we can characterize the Gato derivative by using this auxiliary system in the following, under the following settings shown here. Now the key properties for the auxiliary system is obtained by recent joint work with Professor Antil and Professor Yamazaki. So by using this previous work, we can go ahead the next main theorem 3. For the necessary condition for the approximating optimal control. In this third main theorem, we can show that any approximating optimal control is a solution to the following constraint variational inequality governed by the class of temperature control. And here, P epsilon star and Z epsilon star is a solution to the following backward linear system, which corresponds to the adjoint of the Gato derivative of the cost. Here, we note that the coefficients of this linear system is given by using the solution to the state system correspond to the optimal control. Here we note that for the temperature control, we impose a box constraint. So the optimality condition is characterized by using inequality. On the other hand, for the second component, V epsilon star, we do not impose any constraint. So the optimality condition can be characterized in form of equality. So for the second component, we can say that optimal control coincides with the second component of the linear system with negative sign. However, for the first component, we cannot say such a simple thing. And in order to specify the temperature control, we need some nonlinear operator, such as a projection on the constraint set, capital UAD. Now, by taking the limit of approximating optimal controls, we have the following final main theorem for. Let us define the capital W sub naught as a subclass of H1 functions satisfying the zero initial condition. Then as a limit of the approximating optimal controls, we can find the optimal control of the original system, which is a solution of the following constraint variational inequality. Here, P star and U star is a limiting linearized approximating system. However, in this limiting system, we have some unclear parts denoted by Guzai star and zeta star. And especially zeta star corresponds to the limit of singular diffusion. We cannot say it is a function, it is some distribution belonging to the dual space of capital W naught. Maybe I don't have time to talk about the key point of the proof, and I skip here. And here is a problem in future. My main interest is optimal control problems governed by time discrete state system. And in this issue, I think we can treat eta dependent case of mobility in the original setting of Kobayashi-Wallen-Kata. And for the numerical explanation, I'm very interested in. Now, that's all. Thank you very much for your attention.
Thank you very much for this talk. So I'm sure there are some comments or questions. I'm sure because I have some at least. So maybe I will start. So first of all, can you go to your first slide?
Okay.
Where you have described your system. Okay, so so it's theta is orientation angle. So somehow yes, you admit possible dimensions 2, 3, or 4, but you always kind of assume that this orientation is in one plane.
Yes,
somehow.
So actually it is a 2D problem.
Yeah. I mean, it has this symmetry of orientation, but of course I understand that it's not really a 2D problem, right? Because you don't assume symmetry of your solutions. You only assume that the orientation can be only in the plane. So I wouldn't say it's a 2D, but okay, I just to understand. Thank you. So do you think it's interesting to really do like if you are in 3D, you could want to use real 3-dimensional orientation?
Yeah, there are actually 3D problem proposed by Kobayashi, Warren, and Kata, and it is our next aim, next aim, joint work with Salvador.
Very
My
well.
next-
Yeah, I
Thank
think
you. Good
yeah, maybe if if just the flow of total variation, right, would be done, then it would be maybe easier to do
Yeah.
something like this.
Yes,
Okay,
the
yeah,
expert.
yeah. I had to talk about this, of course. Yeah. So that's the. I also wanted to ask. So you are interested in doing these numerics for it, but you don't have any kind of simulations, anything for now, any particular solutions or anything for this optimal control. Like how
Not
does
yet.
it look like?
Not
No,
yet.
nothing at all.
I'm trying it, but not yet.
I see.
They are not published yet.
Ah, okay, but you are working on that.
Yes, yes, but
I see.
not yet.
Well, I believe it's not easy.
Do you have any
Okay.
idea for the numerical simulation? I want the advice for the efficient algorithm of this state system.
Excuse me.
Problem is how we get the solution. How fast we get the solution of the state system.
Okay, I see. So
But,
control of how good your approximation is.
approximation is this is the approximation method.
Yeah, I understand. But somehow, when you do this discrete approximation, then I understand from what you said that your problem is controlling how good your approximation is. How does it really approximate your solution?
Approximation in the step of discretization, you mean?
Yeah.
Yeah.
I mean, that's what I understood from what you said. Is it correct, or did you mean something else?
Yeah, I adapted the finite element method, but I need a lot of time.
Okay,
To
I
get
see,
the
I see.
solution. So efficiency of the algorithm is
Okay.
distant to my obstacle.
Oh, I understand. Thank you. But okay, well, maybe you can still have some pictures, even if the algorithm is not so efficient. Then
Picture.
would be nice to see pictures for this. How does the control and the optimal evolution somehow look like?
Picture of result, you mean? Picture.
Yeah, like I mean, I understand what you want to calculate is your optimal control, and then when you have this optimal control, you can see how does this optimal evolution look like, right? So this is what you want to calculate in this
Actually,
numerics.
I don't go advanced for the computation of optimal control. I stopped at the step of numerical simulation of the state system.
Just for the state system, I see.
Yeah. Kobayashi Warren Carter provided some results, but they didn't show any process. So I have to try to reproduce their works. But it looks different from their results. So I think my algorithm is not good to follow their computation results.
I see. Okay. Thank you. I saw that Lorenzo Giacomelli raised his hand, but then it vanished. So
no, it's fine. Yeah, I had some minute of mess at home. So,
I see.
but now it's fine. So again, back on the first slide, if it's possible. I had some problems in understanding the modeling behind this system, because maybe, I don't know if you can answer, doesn't matter otherwise, but so this eta is an orientation, and negative eta means disorientation. Then
Yes.
how down, the first question is, let me ask two questions. The first question is, how can you define theta if a phase is disordered? At a disordered phase, how should I imagine theta to be?
Yes.
And the second question is, why is your function alpha decreasing for negative eta and then increasing for positive eta, whereas eta has two different meaning between negative and greater than 1. I don't understand very well the relation between
Yes,
the
yes.
two objects.
Sorry, I didn't mention about the details, so I'm sorry. Let me explain about it. In the original Kobayashi Warren-Kata system, eta r is too much. Eta is supposed to be between 0 and 1. And the physical situation is supposed to be reproduced by vectorial order parameter, eta cosine theta with sine theta. This is a polar coordinate in 2D. So in the original setting, eta is just a modulus of the vectorial order parameter. And eta being 1 means 100% oriented. And eta 0 means no orientation because modulus vanishes. But in our problem, we have forcing. And in this problem, I need to, I cannot realize the constraint. And I need to consider about the outside range of original setting. So this is my additional assumption. But in originally, eta is supposed to be between 0 and 1.
I guess Yoshigiga wants to ask a question.
So, yeah, I have a small question. I think there are many ways to approximation. Of course, in approximation, you approximate total version part in a smooth one, and you are the existence of minimizer also for the approximation problem. And if you change approximation, do you get the same result? Or if your result depends upon the way of approximation significantly or not?
Approximation method, for example, this one.
Yes.
If I have the boundedness of the gradient of the approximating function, then I can get similar result. But for example, P gross type, for example, approximation by P Laplacian, I cannot have the boundedness of this flux, and then it could be another story.
Could you show this 4 main theorems in the next slide?
Main theorem of
list of main theorem, not the rigorous statement. You list the main result, right?
Main result, okay.
Did you list? Yes. This one? No, even previous green one. You list the result. You list the main result. You under four theory.
List
only
one.
sentence.
List.
So
this
if
one?
you slide back, I think. 3 slide back.
2 slides back.
Page 3 or 4? I don't remember. But even before, I think.
This is 3. Maybe different. Main result
I think
starting from here.
Oh, internet is unstable, maybe.
Yeah, there is some problem with connection, I think, with Professor
Maybe
Giga. But I believe Professor Giga means this list that you have showed, really. So
maybe frozen, maybe.
Yeah. It was frozen for a second.
Was,
so maybe it is this list that you have showed with 4 theorems.
Yeah. Yes, 4 theorems.
Then
so
page 4, I think.
Page 4.
Back. 1 slide back.
This one. Yeah, this one. It's exactly this one.
This one is okay. Yeah,
no?
This one is okay. For example, okay. This theorem 2, for example. Okay. This property, looking upon the theorem 2, okay. Does this theorem 2 depend upon the approximation very well? Means if you say if there are some bounds for f epsilon, you still have such kind of things. However, if you lose such kind of bound, you do not expect statement of theorem 2?
Anyway, we can do something. Yeah, we
can
can
do
obtain similar result, but I mean the proof will be completely different.
Proof will be completely.
Yeah.
You guess, even if you change approximation, you may get the same.
In the P-gross type, I have to refer to the Masson's method with Masson's method.
I see. Thank you very much.
Let me ask you a related question.
Yes.
Could you go to slide number 3?
Number 3. Okay.
Yes. Here, what you do is you are approximating the total variation flow somehow.
Yes.
And did you think about addressing the numerics directly? Because you have algorithms like Chambol algorithm to compute the total variation, where you avoid this singularity. Did you think about direct computational approach?
Yes, I recently tried the direct approach, not Chambol's algorithm. And for the application of Chambol algorithm, I'm not sure whether it does work with this weight or not.
That's right.
Chambol's algorithm rely on the duality relation.
That's right.
Linear growth, energy, and indicator function. And that is very beautiful theory. But I'm not sure whether it does work with this weight. But anyway, I have to try in the future. Yeah.
Thank you.
So I wanted to go back to this question that Lorenzo mentioned. So could you go to your first slide?
Yes.
Yeah, so here you have this eta which can go above 1 or below 0. So is it like there is this forcing temperature, and this temperature can somehow force orientation above 1, and then you have to still somehow apply force in the other direction to go again below 1. Is it the case, or?
It depends on the power of forcing. So I need a constraint for the temperature. Box constraint means to control the power of forcing. And due to this box constraint, we can say range of eta is bounded in L infinity sense. So
well, if you are in finite time, you mean it is bounded.
Yes, for each finite time.
Okay, sure. No, I'm just wondering whether you shouldn't maybe consider something different, that if you like reach 1, then you somehow change your system a bit and you can't go above 1, because this is weird. I mean, if 1 is supposed that you are completely oriented, then what is somehow the energy used for if you are already oriented? Or I don't know, maybe it should have a different meaning then. But were you considering something like that? Or I mean, that maybe it should be different, or maybe it is hard for it to be that way?
To keep the range constraint of the original system. Yes, physically, not this. Physically it is required, but here is one. One of the possibilities to add some additional part for the constraint, for example, indicate subdifferential indicator function. Yeah, this is a possible setting. However, in the current step, I don't like the singularity of this time.
Okay.
But we can set up again the problem by using this term, and I think we can obtain some result of the optimal control. But anyway, we need approximation for this singular term. So this would be a double singular system.
I see. So you would need to also pass to the limit with this additional approximation.
Then result would be formulated in weak form.
I see. Thank you. Any other comments or questions?
Yes, if you permit me.
Sure.
I'm thinking about this slide. U
Yes.
is U is temperature.
Yes.
So somehow you heat your container, and you heat the heat sources are distributed somehow within the container. But in practice, how do you wish to achieve this? I would say that if you're going to heat a container, you heat it through the boundary. So I guess you should also consider the control, which is the temperature or heat flux at the boundary.
So you mean there is another governing law of the temperature?
Yes.
Heat equation. Yeah. Yes.
Yet you heat your container by specifying the heat flux at the boundary.
Heat flux on boundary?
Yes.
On boundary. You mean boundary control problem? Is
Yes.
a reality in the practical sense. I see. Heat with boundary control.
Correct.
Boundary control.
Yes.
Yes, I agree with you. Yeah, it's a reality. And actually, we can consider coupling model with the heat equation. The coupling law is somehow links to the fixed cardinal type. And maybe I didn't try it, but we can obtain something on this case.
Okay. Thank you.
Okay.
And I'm curious about another thing. You specify V to be a forcing, which influences the angle of the grain, the orientation angle of the grain. And I'm curious, what is this in practice?
Very good question. This is mathematical term for me. As a mathematical problem, we can add it, but in practical sense, I think it doesn't make sense. But mathematically, we can do it. So if we don't like it, then we just remove this one, and then we can apply our general theory.
Okay, but I suppose technically you can more or less work just with temperature, maybe some pressure or something. But I suppose you can still just having control in this first equation by temperature can somehow help you with adjusting orientation, because when you have big disorientation or small somehow, I mean small value of eta, then I guess it's easier for orientations to align. No, is it the case? Typically,
for small eta, the free boundary may nucleate.
Nucleate,
and the minimization point of eta would control the movement of grain boundary.
Okay.
So
yes, so by
please.
I see. No, okay. So I suppose that's already something, but never mind. So maybe we don't have much time, but I wanted to ask you: do you have some actual, say, do you communicate with these people who really do it? I mean, you got a picture from this UBE scientific analysis laboratory. Do you somehow communicate with them about what do they need or something?
I don't have a connection with UBE scientific laboratory. This is comes from the advertisement picture.
I see.
On the website.
Okay. Well, any other comment or question? This would be probably the final one. Okay, if not, then I guess let's thank Professor Shirakawa again for his talk. And now we will have a talk by Wojtek Górny, if I'm right.
Yeah, I suppose
Wojtek,
so.
are you here? Okay,
Yeah.
very well. I suppose you have some slides probably, so
Yeah.
you might want to share them with us.
I'm trying. Okay. Is it visible? Yeah.
Yes.
Okay. And one more thing, if I change to a picture, it's also visible. Okay. So not only
Yes,
the
it is
slides.
also visible. Great.
Okay.
But just let us wait. Ah, no, now we have 11:20. So I think that's the right moment to start. So now we have Wojciech Górny from still University of Warsaw, and I believe since 3 days, also University of Vienna, who will speak about optimal transport methods in the least gradient problems. Please go ahead.
Okay. Thanks. Good morning, everyone. I will speak, as Michał said, about how to employ methods that were originally introduced in order to solve the optimal transport problem in the least gradient problem. So to start, let's say, what is the least gradient problem? Supposing that we have an open bounded set with Lipschitz boundary, we have some boundary datum, which is in L1 on the boundary, and we want to consider the following minimization problem. We minimize the integral of the length of the gradient of a function with respect to this boundary condition. So the natural space in which we look for minimizers of such a problem is the BV space. It also has a natural way how can we understand the boundary condition. So because traces of BV functions on the Lipschitz boundary are well defined, so we will understand the boundary condition as a trace of the BV function, the trace of u equals f. The Euler-Lagrange equation, which corresponds to the solution to solving this problem, is the one Laplace equation. So minus divergence of du divided by the length of du equals 0 in omega, and du attains the trace. Because this equation is degenerate, there are some ways how to understand it, give it a proper meaning. It was done a few years ago by Mazon-Ross and Segura de Leon. In particular, with understanding the boundary condition in some weaker sense than the trace sense. But here in this talk, we will keep the trace sense throughout the whole talk. Okay, as we can see from the one Laplace equation, if we take u to be a characteristic function of some set, then this equation corresponds to the fact that the mean curvature of the boundary of this set disappears. So this problem is naturally linked to the study of minimal surfaces. Also, among other things, it's linked to optimal design, conductivity imaging, and in 2 dimensions to optimal transport. And in this talk, we will focus on these links. So throughout most of the talk, we will stay in 2 dimensions. Okay, so first, let us review what are the standard assumptions and standard results in the least gradient problem. First thing that needs to be said is that because the problem is related to the study of minimal surfaces, because boundaries of super level sets of solutions to the least gradient problems are minimal surfaces, the problem depends very much on the geometry of the domain. So in order, for instance, for the trace to be achieved, we cannot have, so to say, level sets of a candidate of a solution stacking on the boundary. So the boundary cannot be locally area minimizing with respect to interior variations. So different authors introduce some versions of these assumptions, like here I wrote strict convexity of omega or positive mean curvature of the boundary. Because we will stay in 2 dimensions, I will just stick with strict convexity of omega. Okay, assuming it, what are the standard results we can get in the least gradient problem? So first thing is existence of solutions for continuous boundary data, or even under a slightly weaker assumption that the boundary datum is continuous almost everywhere with respect to the Hausdorff measure on the boundary. In particular, in 2 dimensions, this includes BV boundary data, because the one-dimensional BV space on the boundary has only at most countably many jumps. Any function from the one-dimensional BV space on the boundary, so it's continuous almost everywhere. The second thing is uniqueness and continuity of solutions if the boundary datum is continuous. And the third thing are some results on regularity of solutions. Actually, it's difficult to get some global regularity results. For instance, because even for smooth boundary data, it may turn out that the solution is only Lipschitz. So there are mainly 2 types of regularity results that were proved in this problem. One of them is Helder regularity. So assuming that the boundary datum is Helder regular, we can prove that the interior datum is also Helder regular with some worse exponent. And the other thing is generic smoothness, so to say. There are some results about if the boundary datum is smooth, then there exists an open dense set on which the solution is C4, C5, depending on the dimensions, but it's away from some set on which the solution is maybe only Lipschitz. An important thing to note here is that there is no similar results for Sobolev regularity of solutions using the classical approach. So assuming that the boundary datum lies in some Sobolev space on the boundary, we weren't able until recently to prove that the solution is also lies in some Sobolev space inside the domain. This will be achieved using transport methods. Okay, so how does the relationship between the least gradient problem and the optimal transport problem look like? There is an almost equivalence between the 2 problems in 2 dimensions, and it is achieved in 2 steps. The first step is equivalence between the least gradient problem and the Beckmann problem. So suppose that the domain is convex, then a few years ago in a paper by Professor Rybka, Ahmad Sabra and myself, it was shown that the least gradient problem is equivalent to the Beckmann problem. So we want to minimize the length, the integral of the length of a vector field with 0 divergence, such that the boundary condition is as follows. The normal trace of this vector field equals G, where G is the tangential derivative of the boundary datum in the least gradient problem. The natural space in which we look for solutions to this problem is when the vector field is a vector valued measure defined on the closure of omega. Okay, so what do I mean by equivalence here? It's not a true equivalence, but it's an almost equivalence. It's given in the following sense. The infimel values coincide. If we have a solution to the least gradient problem, then we may construct a solution to the Beckmann problem. And if we have a solution to the Beckmann problem, which gives no mass to the boundary, then we can construct a solution to the least gradient problem. So it's an almost equivalence between the 2 problems. And formally, it is given in a very simple way. So the solution to the Beckmann problem, the vector field P, is a rotation by 90 degrees of the gradient of a solution to the least gradient problem. Okay. The second step is actually well known for some time. It's equivalence between the Beckmann problem and an optimal transport problem. Again, if the domain is convex, the Beckmann problem is known to be equivalent to an optimal transport problem, where the source and target measures are located on the boundary. So here, the optimal transport problem is written as follows. We want to transport a measure G plus onto a measure G minus with Euclidean cost. Here, because we want to transport a measure to a measure, we need to assume that G is a measure. G here is the boundary datum in the Beckman problem. So it's the tangential derivative of the boundary datum in the least gradient problem. So in other words, we assume that the boundary datum in the least gradient problem lies in the BV space. So its tangential derivative is a measure, and we may here say that the optimal transfer problem here is well defined. And these two problems are truly equivalent. So from every solution to the Beckman problem, we can construct a solution to the optimal transport problem, and in the other direction. And also, if sigma gamma is the transport density corresponding to some optimal transport plan gamma, then this transport density equals the length of the solution to the Beckman problem. Okay, this will play a role in a minute. And these two equivalences were laying on the table for some time. And after a visit of Professor Rybka to Orsay, these two results were put together by Samer Dweik and Filippo Santambrogio, who noticed that there is an almost equivalence between the two problems. So we might employ optimal transport methods in the least gradient problem. The main idea is as follows. I will first write the idea and then present a picture to give some impression how it works. So for f, which is in the BV space on the boundary, we may represent the least gradient problem as an optimal transport problem, where the source and target measures are equal to the positive part of the tangential derivative of the boundary datum in the least gradient problem and the negative part of the tangential derivative. Also, in this formulation, transport rays correspond to level sets of the solution to the least gradient problem. We'll see a picture in a second. The thing that will be crucial in the rest of this talk is that the equivalence between the least gradient problem and the Beckman problem was whenever we have the solution to the Beckman problem which gives no mass to the boundary. So also whenever the optimal transport plan gives no mass to the boundary. So all the transport rays lie inside the domain, which means that proving existence of solution to the least gradient problem might be easier in some settings other than strict convexity. We have another method that if we inspect it more closely, then maybe we can use this fact to prove existence of solutions to the least gradient problems on non-convex domains. Another thing is that this actually is just works for replicating the results in the least gradient problem, but there are also some new possibilities that arose. The first thing is that we need less than continuity of f for uniqueness of solutions. We only require that either the positive part of the tangential derivative or the negative part is atomless. So yeah, continuity of f would mean that both of these measures are atomless. We only require one of these to be atomless. And the main thing, and actually why Dweik and Santambrogio consider this problem, is that because on a formal level, the transport density equals the length of the solution to the Beckman problem, which equals the length of the gradient of the solution to the least gradient problem. If we prove LP estimates for the transport density, they correspond to W1P estimates for the solution to the least gradient problem. And actually, Dweik and Santambrogio were working for some time on LP estimates for the optimal transport problem, which goes from boundary to boundary. So they, in this way, they proved the first Sobolev estimates for solutions to the least gradient problem in terms of the W1P norm on the boundary, because the W1P norm on the boundary corresponds to LP estimates on the tangential derivative. So proving LP estimates in terms of LP estimates of the tangential derivative corresponds to W1P estimates for W1P boundary data. Okay, so now it's time for a picture. Okay, so assume that the boundary datum is as follows in the least gradient problem. and that here, let's minimize this. Here, the boundary datum equals 1 on this arc. On this arc, it equals 0. Here we have a jump on this blue dot.
I don't see any picture.
You don't see any picture. You still see the presentation.
Yes.
Okay. So I guess I have to do it.
You should probably stop
Okay.
sharing.
Stop sharing and move to another screen. Okay.
That's correct.
Okay. And now?
Perfect.
Okay. So here we have the boundary datum in the least gradient problem, which is equal to 1 on this arc on the top, equal to 0 on this arc on the left. Here is a jump at this blue dot from 1 to 0, and it grows from 0 to 1, let's say linearly in the angle here on this arc on the right. So how do the transport rays look like in this case? In the what does this correspond to in the optimal transport problem? Okay, so here the boundary measure is 0 because the function is constant. Here the boundary measure is 0 because the function is constant. Here it's something proportional to the Lebesgue measure. Okay, sorry, Hausdorff measure on the boundary. Yeah, this is the tangential derivative positive part. And here the tangential derivative negative part is the Dirac delta at this point. Okay, so how do transport rays look like? Like this. This whole arc is transported onto this single point. And how, okay, so this is the solution to the optimal transport problem. The transport rays look like this, but also the solution to the least gradient problem looks in the same way. So here the solution equals 1, here the solution equals 0, and here whenever we have a value t at the end of this transport ray, then along the whole transport ray the value of the solution equals t. So yeah, transport rays corresponds to level size of the solution, roughly speaking. Okay, let's save changes, stop sharing and go back to the presentation. Okay, can you see the presentation?
Yes.
Yes, okay. So we can actually extend this framework in a few ways. So the rest of this talk will be based on my results together with Samer Dweik from the University of British Columbia now. Okay, the first two are not yet online, so I'll just advertise them. So the first thing is that we can endow R2 with another distance, for instance, generated by a smooth weight, and do something in that case, in particular the W1P estimates in this case. And the second thing is prove the equivalence between the least gradient problem and the Beckman problem on contractible domains, not only convex, but on contractible domains. Part of most, I mean, the second dot and most of the first dot is done already, but it's not yet online. So I will focus on the third thing, which we did last year. Okay, so for equivalence between the and the optimal transport problem, we do not actually need convexity of the domain. We need that there exists an optimal transport plan such that all the transport lays for it lie inside the domain, that it gives no mass to the boundary. So we could let go of the convexity assumption and in turn introduce some conditions on the structure of the boundary data. So possibly we could consider domains which are not convex and replace the convexity assumptions with some structure assumptions that I will present shortly. For instance, we are able to consider a situation on annuli, where by an annulus I mean a strictly convex domain with a removed strictly convex domains, which are not even contractible, the boundary of the annulus is not connected. Okay, so there are two things that we need to take care of. And the first one is that we do not have the equivalence between the least gradient problem and the Beckman problem as advertised in the first part of the talk, because of what I will see I will show an example in a second. So I'm stopping sharing. Okay, I move back to the picture. Okay, so assume that the boundary datum in the, can you see the picture?
Yes. Yes.
Yes, okay.
Yes.
Assume that the boundary datum in the least gradient problem equals 1 on the outer circle and equals 0 on the inner circle. Okay, what does the boundary datum in the Beckman problem look like? So the tangential derivative of this is 0 on both circles. So the solution to the Beckman problem, this is the Beckman problem, the normal trace equals 0, the divergence equals 0, so the vector field, which is the 0 vector field, solves this problem. Okay, so because we have this formal equivalence, it also means that u is constant. But if u is constant, it cannot satisfy the boundary condition in the sense of traces. So we need to account for such a possibility and modify the relationship, prove another version of the relationship between the two problems. Okay, I'm going back to the presentation. Okay, so we need to allow for, let's say, vertical translations on connected components on the boundary. So we have an equivalence, we can prove an equivalence between the Beckman problem and the following variant of the least gradient problem, where we minimize the integral over omega of the length of the gradient as in the least gradient problem, but with a different boundary condition, that the tangential derivative of the trace of u equals g. G is the boundary datum in the Beckman problem. So we allow for shifting the boundary values in the least gradient problem by a constant on each connected component. Okay, which gives us some technical difficulties later when we try to solve the least gradient problem, but not much. We just have to account for the situation as in the picture, as in the previous picture. And the second thing that we need to take care of is to ensure that actually there exists a solution to the optimal transport problem which gives no mass to the boundary. So we need to introduce some admissibility conditions for boundary data. Okay, so now I will present a third picture. Okay.
We see it.
Okay. Here we have a third picture. Okay. First, we prove a priori result that if there exists a solution to the least gradient problem with the boundary data f, then f can change monotonicity only finitely many times. No.
Sorry, Wojtek, there seem to be some problems with the connection.
Your screen froze.
Yes. I don't know if you hear us. Maybe I will try to contact Wojtek by an external channel, if I can. I'm not sure I'm able to.
Okay, am I back or am I not back?
Yes, we hear you now, Wojtek. Hello.
We can hear you. We don't see
Can you hear me?
Yes, we can hear you.
You can hear.
Yes, you're back.
Okay.
Perfect.
Yes, there are
Okay.
still some problems
So-
with the connection from time to time, but okay. But most of the time we can
Okay.
hear you and we can see you.
But okay, and you can see the picture in
No.
particular.
At the moment, we look at your presentation.
Okay, so let's go back to the picture. Okay, can you see the picture?
Yes.
Yes.
Yes, okay. So first we prove a priori that the boundary datum on the inner circle, if there exists a solution, can change monotonicity only finitely many times. So the structure conditions we introduce are as follows. We separate the inner circle into finitely many intervals of monotonicity. So here for the picture, I chose 2 intervals of monotonicity, and we introduce a structure assumption as follows: that for each on the arcs of monotonicity on the inner circle, there is a corresponding arc on the outer boundary, on which the total variation changed by the same amount, and that from each point of the inner arc, we can see every point from the other arc. So it's actually a visibility condition, so that we may freely move the transport trace regardless of how the solution, how the boundary datum looks on each monotonicity intervals. So we move from the convexity assumptions. Here we introduce an assumption which says how do the intervals of monotonicity look like. And then we give a detailed discussion of the assumptions to say that they are not actually, so we provide is violated, then the existence of solutions may break down. Okay, so here, for instance, the conditions are mostly about visibility, and they are to ensure that the transport rays do not leave the domain, so that we actually transport something from this part to this part, and from this part to this part, and we do not leave the domain. Okay, so I'm coming back to the presentation for the final slide. Okay, can you see the presentation?
Not yet.
Okay, let me do this again. Okay, and now?
Now it appeared.
Now it appeared, okay. So for the final 2 minutes, let me state a theorem. So there's actually a theorem in this presentation. Okay, as I said, it's a joint work with Summer Dweik from the University of British Columbia. Suppose that omega is an annulus, so a strictly convex domain minus a strictly convex domain. And under certain admissibility conditions on the boundary datum of the type I presented before on the picture, there exists a solution to the least gradient problem. There are also 2 additional features. So firstly, if one of the measures, the tangential derivatives, the positive part or the negative part is atomless, the solution is unique. And also we may get the exact same or actually even better Sobolev estimates for the solution here, because the Sobolev estimates obtained in the strictly convex case worked for P smaller than 2, unless there are some additional conditions imposed. The reason for this is the following: that in the proof, we actually separate the part close to the boundary and away from the boundary. And the part close to the boundary, if the domain is strictly convex, may this estimate may fail for p larger than 2.
We don't hear you.
Yes, you're frozen again. Did you do anything last time, Piotr, when he vanished?
And now, can you hear me?
Okay, now we can hear you and we can see you.
Good.
Okay.
Welcome back.
Okay. So as I don't know at which moment I froze, so let me just say this final thing, that we can prove Sobolev estimates even better than we could in the case when the domain is strictly convex, because of our admissibility conditions. The admissibility conditions, which are almost required to provide, if either of the conditions is violated, we can provide some types of examples where the solution doesn't exist. They are sufficient and almost necessary. They force they force some structure of the solution, which actually makes the LP estimates easier, and it makes the LP estimates for p greater than 2 possible, which were not possible in the strictly convex case. Okay. So thank you very much, and that's what I want to present. Thanks for
Thank you very much, Wojtek. So are there any comments or questions? Please, Doug. Maybe I can start with some easy ones, just to get them out of the discussion, because, okay, so first of all, you said in this last slide, or the one when you stated your theorem, that you work in annulus, but you said that you mean a strictly convex domain minus a strictly convex domain. So yeah. Is it important that it's exactly the annulus or not?
No, I mean, it doesn't matter how the domains are located with respect to each other. You can have, they do not have to be concentric circles, or what is usually meant by the annulus.
Okay.
It can be anything. Actually, you can remove even more domains from the inside, but then the admissibility conditions become horrible.
Simply. Okay, I see.
But the equivalence can like this can still be proved if we remove more parts inside and not only one.
Mm-hmm. Okay, and I also have a second, maybe obvious question. So this is all awfully two-dimensional. I mean, but on the other hand, it could seem that you could also have some kind of connection between these least gradient problems and optimal transport in higher dimension. So how is it?
Not really, because let me go back to this equivalent. Okay, the equivalence between the Beckman problem and the optimal transport problem stands in higher dimensions also. But there is a problem with this part. Okay, the equivalence is given here by rotation.
We don't see your presentation. Sorry, Wojtek.
You can see my presentation?
No.
We are seeing you.
Okay. Yeah. Okay, so without the presentation. The equivalence is given in the following way. The solution of the Beckman problem is a rotation by 90 degrees of the gradient of the problem. And actually in higher dimensions, if you want to make such a thing, it would correspond to the fact that the vector field in the Beckman problem is the rotation, the vectorial rotation, the rot operator, and not, so it actually doesn't have the gradient inside. It has something different. It has a different differential operator under the gradient. If, for instance, you want to prove LP estimates or something like this.
Okay, I see.
You have
so
the
it's just a
vectorial rotation and not the gradient.
Mm-hmm. I see, thank you. Okay. So for the moment, maybe I will let others ask questions.
Let me start with a comment. Wojtek, you called your. Could you go to the first slide or
Yeah.
the slide with the results?
The
Yes, further, please.
classical approach
Yes.
results.
Oh, the first is that existence of solutions for continuous for data which are almost everywhere continuous on the boundary.
Yeah.
This result is maybe 5 years old, so I wouldn't call it classical, but I may call it well known. So this is
Yeah, but I wanted to stress that this is obtained using the classical methods, the geometric measure theory methods, and not using optimal transport.
Okay. And let me ask you a stupid question.
Yeah.
Do you impose any constraint on the number of monotonicity changes on the inner part of the boundary?
No, but yes. I mean, the visibility you have to have visibility between the inner boundary and the outer boundary for some monotonicity arcs, and this, in fact, is a condition on the number of the monotonicity intervals, because if you have, for instance, these circles quite far apart, then you can only fit one interval. You can only fit 2 intervals on the inner circle of monotonicity. If they are close to each other, the annulus is very thin, you can fit a lot of them. So it's an indirect assumption on the number of monotonicity intervals.
I see. So you cannot have infinitely many oscillations, indeed.
No, we can prove a priori that you cannot have infinitely many oscillation.
And let me ask you another question. You have a new tool. So what are the possible new problems you can tackle with this new tool, which are not accessible with the classical tools? Do you have an idea?
Okay, I can say something that we are currently working on, which is LP estimates for the transport density, so WNP estimates for the solution. If we have here not the least gradient problem, but the least gradient problem with a weight, with positive C2 weight. So this C2 weight generates some Riemannian structure on the domain, and we want to attack if we can get also some more regularity in this case, because actually in this case there is not much regularity. I mean, the only known regularity results in this case are continuity for continuous boundary data. Nothing else is known. So this would actually contribute first regularity result.
I see.
Okay, so
I wonder if Marta has any question. Apparently not.
or somebody else.
Or somebody else. Like Salva.
Good shot, I would say.
Oh,
Or
yeah.
Mathon. We have Mathon.
Ah, Mathon. They are experts.
Hello, I have no questions. I am very glad that that Wojtek has continued with his study since his PhD with 2 new results. I am waiting for see them online.
Okay, so that was not a real question, but we will let it pass. You will not be thrown out, Salva, for that. Yeah, but I actually wanted to ask maybe something different. So you applied for now. You applied this optimal transport to this non-convex situation. You have strictly convex domain minus strictly convex domain. So something like this cannot be handled with your previous methods, because
no, completely not, because the previous methods how to say, the previous methods constitute mostly of outright construction of solutions.
yes.
Or approximation.
Sorry, we have some noise here. I will try to diagnose this noise. Where is the noise coming from? Noise. I don't know.
Okay, so the previous
stopped.
methods are actually only two. First is proof existence for continuous boundary data using an outright construction. And the second thing is approximation with continuous boundary data if the boundary datum is not continuous, at least if you want to keep the understanding of the boundary datum in the sense of traces. And this first method really requires the domain to be convex. The proof very heavily uses the non-minimality of the boundary. I can see anyways how we can replace it. I mean,
uses what? Excuse me again. Uses
the fact that the boundary is not locally area minimizing. Even if the domain is convex in 2 dimensions, you could ask an expert, Professor Rybka, because he works in this for some time. You have a problem, these methods fail, and you need to approximate the convex domain by a sequence, well-chosen sequence of strictly convex domains. For an annulus, you can't do that, simply.
Well, sure. But you need that assumption when you are actually constructing the minimizer, you're saying? Yeah. Or is it to prove that what you are constructing is the minimizer?
During the construction of the minimizer. Because you, more or less, you solve the minimal surface equation at one step, and you require for it convexity of the domain in order to get the solution. You solve the minimal surface equation locally for all the level sets, and if you want them to stack in a correct way to form actually a function, a BV function, then you need for this convexity of solution, convexity of the domain.
I see. Okay. Thank you.
I would like to welcome the participant from South America. It's 7 o'clock in the morning, so we really appreciate your efforts of coming here.
Yes, so I'm wondering whether I should stick more to the old schedule where we started at 12:10, or maybe we can start a bit sooner.
No, the schedule is the next talk starts at 12.
At 12, so the schedule is roughless, and this means that we should probably start. Yes. Okay, we just wanted to give some time to South American participants. Okay, but since the schedule says the next talk is at 12, then I think, unless there are some questions, some final question to Wojtek or a comment.
I would like to thank the speaker.
Yeah, if not, then we thank Wojtek. And now, please, Professor Yamamoto, if you are ready.
Yes. Yeah.
Yes. Please share your.
Yeah, but a bit strange. I cannot change to video.
Sorry.
Stop. Yeah, something.
No. Now, yes. Now I asked you to start video, and this should allow you to.
Okay.
Okay.
Now. Okay, then
Hello?
I will change. Just one question. Immediately, can I start or?
Yeah, sure. I
Okay.
mean, but please, we want to still officially introduce you. So
Sure. Then I can start to share
yes.
the display. Okay. Something wrong. Maybe okay.
Perfect.
I hope everybody can see the display with the cover page of my presentation.
Yes, we can see it.
I hope the size is okay. Not too small, not too big.
Yeah, it's perfect. So
Yeah,
okay. So
now I'm
let's
ready.
start then. Yeah, now we have the final speaker of this morning's session, Professor Masahiro Yamamoto from the University of Tokyo, and also an honorary member of Academy of Romanian Scientists, who will speak about some recent results concerning uniqueness and existence of solutions for some fractional partial differential equations and some inverse problems. Please go ahead.
Thank you very much, Chairman. First of all, I would like to thank Professor Piotr Lyubka for inviting me to this very fun. Sorry, something wrong. Sorry.
Yeah. There was some problem with the connection. I hope it does not stay like that.
Okay. Okay. It looks some trivial.
Okay.
Okay. Then.
Sorry, but the presentation is not on, so you need to share your screen again.
Okay. Okay. Wait a moment. Okay. Just a moment. Oh, strange. Okay, maybe I will close once again. Okay, maybe here. Okay. Voila. I hope okay.
Yes. Now it's your presentation again.
Okay, thank you very much. And secondly, I'd like to apologize because with this kind of title, anybody can talk for anything. too general. I'm very sorry. But I will of course be focusing. And also, I should not request everybody to keep the intensive attention to every page. But however, the next page is one of the most important, namely, this is my rough idea. Also, I would like to make some announcement of the new book with my Polish colleague, Professor Adam Kubica, and Katarina Listzewska, Dr. Listzewska. And very soon it will be published, but not yet published. Then mainly the contents of my talk is based on this framework constructed in this book. This book will be appear from Springer. Oh, sorry. Then okay. Then the purpose of this book provides some convenient framework, theoretical framework for time fractional partial differential equations. Then the point of my talk is explanation how it works. Okay. Then I plan to the following contents. Okay. Anyway, then if you have some additional questions in appendix, I'm ready to answer some questions, some other questions, namely, which will happen with other frameworks. But in principle, I will not touch, then I will follow my own theoretical framework. And also, this is an apology. That is my favorite word by Richard Feynman. Many things no, but a few proved. Then mostly you are a specialist for fractional calculus and fractional differential equations. Then I will present some results, but most probably you know already most of them. But I will prove within this kind of framework. Okay, then. The content is as follows. Okay, a little bit many sections, but I will try to minimize my presentation time, and also based on the joint works with my colleagues, also from China and from Italy. Okay, then the first part is fractional calculus part, mostly definition of fractional derivatives. Of course, this is absolutely classical topics, but by some reason, I need some necessity to revisit. Okay, then please let me use this kind of notation. Sorry, this is not conventional letters, but dt alpha means Caputo derivative. And if alpha is between 0 and 1, this is a very traditional, and I think everybody knows the definition of the Caputo derivative. Of course, gamma is a gamma function. Then we have the quests. What is the property, calculus property for such kind of fractional derivatives? Of course, since many years, plenty of results have been done. But just shortly, I would like to mention, for example, this kind of repeat derivative, what will happen, or many things, also the fractional differential equations, how to formulate initial value problems, and the regularity of the solutions, etc., etc. Then for this kind of requests, I would like to propose the following framework, namely definition of fractional derivatives. This is not perfectly new, in a sense, adjusted to the traditional fractional derivatives. The tendency is that nowadays still many creations of new fractional derivatives. Some of them is wrong and some of them is correct, but I don't want to create new fractional derivatives, but just a bit modification. This is a viewpoint. Okay, then some small preparations. 0C1 is the subspace of C1 at the left end point, V0 is 0. This is like a kind of initial condition, but anyway, V0 equals 0. This means that with suffix 0. Then J beta is a usual Riemann-Liouville integral operator. Beta is any positive number. Then first result is just the property of J alpha. And for the moment, alpha is between 0 and 1. And later we will generalize. But anyway, J alpha is isomorphism from L2 space to H sub alpha. Injective and surjective, and also the norm equivalent. Okay, H sub alpha is a bit unusual over space. But already yesterday, Professor Kubica introduced, but say H sub alpha is same, alpha is smaller than 1/2, is a classical Sobolev-Slobodetsky space. Alpha equal 1/2 comes from some complexity comes from the interpolation, but anyway, with extra constraint. And alpha is greater than greater than 1/2. Since H alpha, the Sobolev-Slobodetsky norm can make sense, the trace, then in that case, we will attach V0 equals 0. This is a definition of the space of H sub alpha. This is a basic space for our approach. Then the norm is naturally defined like that. Only small difference is that alpha equals 1/2. We must take into consideration this kind of extra term. Then J alpha is isomorphism between L2 to H sub alpha. This is not trivial, but one can prove. Then, sorry, something wrong. 1 and 2, yeah, sorry. Then the second is other characterization. Okay, sorry. Okay, this is 3. Then now, thanks to this isomorphism, let us define our derivative is inverse of J alpha. Then naturally by the definition, domain of this so-called fractional derivative in our sense is nothing but H sub alpha. In other words, the range of J alpha. This is a formal definition. Then after that, we can prove that the proof is not so complicated, but this defined fractional derivative is the closure of Caputo derivative with the domain 0C1. This means that we will consider Caputo derivative with V0 equals 0. Then we will take the many closures, closed extensions. Then we take the minimum closed extension, which is nothing but our derivative. Then that is a basic property. Then this is a bit agree. And in principle, this notation indicates with the domain. Namely, the domain of this is H sub 1, not H super 1. Therefore, I will not use so many times simultaneously, but in principle, by this we mean usual derivative in, say, distribution sense. But this notation means that our definition. Then maybe I will skip the remark. This is not so important, but okay, maybe the first part is first one is useful. Namely, in this our fractional derivative v L2 norm is equivalent h sub alpha norm, and also especially alpha is greater than or equal to 1/2 h sub alpha, our Sobolev space is not same Sobolev-Slobodetsky space, because according to alpha, we must take care additional condition. This is by the Sobolev embedding. If alpha is greater than 1/2, this space is embedded into the continuous function. Therefore, if v is in H alpha, v0 equals 0. And mostly during my talk, I will not touch H super alpha, only H sub alpha. This means that almost always, we will consider Sobolev space with some boundary condition at t equals 0. But it is not impossible to define in this framework, the fractional derivative for general H super alpha. But this is not so main topic. Okay. Then next is we would like to extend such fractional derivative to general alpha positive, not necessarily between 0 and 1. But the extension is quite natural. Namely, if alpha positive is represented, this is a part of the natural number plus sigma, say, fractional part between 0 and 1. Then Hm plus sigma is naturally defined after taking m times derivative. M is a natural number part of the order of alpha. Then after taking natural number part times derivative, this should be in H sigma. This is non-natural part of the order of alpha. Then this is, if we admit the first theorem, those theorems are immediately can be proved. Namely, m plus sigma is isomorphism between L2 to H sub m plus sigma. Then after that, we will define fractional derivative just the inverse of integral operator. Then also 1-3 theorem is just the rewritten form of this, because we will take just algebraic inverse. Then by the isomorphism, algebraic inverse is also isomorphism. H beta to H alpha plus beta. Sorry, H alpha plus beta to H beta. Then this is quite natural, because after taking alpha times derivative, the derivative order is decreased to beta. This can be correct for any alpha and beta positive. Okay, then some also the basic theorems can be proved rather easily. The first of all, repeat derivative formula. But the point is that we will consider with always boundary condition or initial condition t equals 0. H alpha beta, then always this is correct. If we will not consider this, some other condition, some extra condition is necessary. But within H sub alpha, such family of the Sobolev spaces, everything is okay. And also Laplace transform the same, namely blah 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 blah. But of course, some behavior at the infinity is necessary. But the point is that in general form, some other terms coming from initial value. But since we will consider H alpha, then those initial values are 0. Then only principal part. Then also the coercivity can be proved. In principle, the proof is not so complicated. At first, we will prove C1 function vanishing at t equals 0. Then we will take a density argument. Then H alpha like that. I think one uniform form, one unified form. And also, since our fractional derivative is defined by the inverse of integral operator, therefore, very simply, we can characterize adjoint operator of fractional derivative. Like that, roughly speaking, especially the domain of adjoint is a bit delicate issue always, but in this case, just the domain is characterized H sub alpha, but we must exchange two endpoints, 0 and t. Namely, tau is just exchanging left endpoints and right endpoints. And that kind of adjoint operator is very useful for considering optimal control problem or something like a transportation method for non-homogeneous boundary value problem, but I will not touch at all that. Okay, then anyway, this is a motto. I believe that our defined fractional derivative makes our fractional lives easy. But the point is that not completely new, namely just in general, not same as a Caputo derivative, but in some suitable domain, then our fractional derivative coincides with the Caputo derivative and also Riemann-Liouville derivatives. But, okay, maybe I will skip that part. Okay, then fractional ordinary differential equation, but maybe I will skip, but I would like to, okay, maybe that time, for saving the time, I will skip. Then the final section, namely fractional partial differential equations. Then this is a basic elliptic operator. Not always we will consider this, and in some cases we will consider only autonomous case, namely the coefficients are t independent. T does not depend on t, but general form minus at is like a t dependent uniform or regular elliptic operator of the second order. And also here I don't pursue the minimum regularity for the coefficients, but roughly Aij, Bj, C are more or less C2 class. Of course, this is not optimal regularity, but anyway, say smooth regularity, and also I will not touch degenerate case, uniform ellipticity. Then basic result is as follows. Then in formulation of initial condition is always needs some cares. Then here, this is our fractional derivative. Then the fractional time derivative part, we will take this form, u minus a and fractional derivative. And that part is just conventional, just say my elliptic part plus non-homogeneous term. And for the moment, we will consider homogeneous Dirichlet boundary condition. Therefore, for almost all t, u is in H10. This corresponds, of course, boundary condition. Then initial condition does not appear explicitly, but that part requires, namely, u minus a must be in the domain of this. U minus a is in the domain of the fractional derivative. The domain of the fractional derivative is h sub alpha. Therefore, this is like a initial condition. And also, most of you can remember that this is not so different from the conventional way. Namely, conventional way is that we will replace that by the Riemann-Liouville operator. Then u minus initial value. In that sense, same. But we are considering the domain, namely h sub alpha. Okay, then after that, we can prove that this kind of basic unique existence result. For the moment, two categories. Non-homogeneous term is L2H minus 1. Initial value is in L2. Then we can prove the unique existence of the solution U is in L2 H10, and moreover, U minus A is in H alpha H minus 1. Of course, including a priori estimate. Second category is that a bit more regular F and a bit more regular initial value, say H10. Then the regularity can be lifted up. Then the proof is quite conventional way, namely Galerkin method and the coercivity. And the coercivity already was shown in some theorem in H sub alpha. Then, of course, this is a basic result, and already there are many results, including Professor Riko Zahia. Then, by the way, what will happen, at least I would like to touch the formulation for general alpha. Within this framework, if alpha is greater than 1, reasonable formulation is like that. Maybe I think from the physical viewpoint, it is very sufficient for us to consider alpha is maybe smaller than or equal to 2. But general thing is, general formulation is like that. And also, except for the details, the point is that initial conditions, of course, we need more initial conditions if alpha is bigger. But such initial conditions should be installed, this kind of form within our framework. Then quickly, I would like to touch very classical solution formula. Solution formula in a special case is quite useful. Special case means that A of T elliptic operator is T independent and also symmetric, namely no first order term, and keeping some sign, namely zeroth order term C is non-positive. In that case, there exist eigenvalues, and including the multiplicity, let us denote by phi n the orthonormal eigenfunctions, say phi 1, phi 2, blah, blah, blah. Then we'll put beta-Leffler functions E alpha beta. Then, especially between alpha is between 0 and 1 and some regularity, the solution is represented by the Fourier's method, like that. Then, of course, this is not a new formula, but within this our framework, we can prove that U minus A is in H alpha. And also the regularity is that. Then this means that basic theorem can guarantee the unique existence of the solution to initial value boundary value problem. Then this special case, this theorem can give the representation formula of the solution. Of course, we need Mittag-Leffler functions and so on. Then, by the way, the proof for that regularity is not very trivial, because the regularity of F is just L2 in time t. Therefore, we must lift up the regularity in time t to H sub alpha from L2. This is just a central point, but this is maybe intuitively quite understandable, because that is a Mittag-Leffler function, but we can make a Taylor expansions. Then here is more or less T minus S alpha twice alpha and so on, so on. 3 alpha, 4 alpha. Therefore, if formally thinking, this is like a series of J alpha, J twice alpha, blah, blah, blah. But already we have proved that J alpha is isomorphism from L2 to H sub alpha. Therefore, like that. Of course, we must take care of the convergence sense. But anyway, roughly and formally, we can prove that this is in range of J alpha. But anyway, I should hurry up. Then I added that page today. Namely, yesterday somebody seems interested in some improvement of the time regularity. Then this is other representation of that, namely optimal regularity for T positive. Then 2 cases. This is a joint work with Professor Floridia from Reggio Calabria and Professor Li Ziyuan from Shandong and myself. Okay, at first, alpha is between 0 and 1, and A is T independent, general, not necessarily symmetric. Then we, of course, without non-homogeneous term, then that case, we can prove that norm equivalence. This is the initial value, like an initial value. L2 norm is equivalent H2 norm at any positive capital T. This means that this case, time fractional diffusion equation is absolutely time reversible. Of course, we must take a stronger norm, but only +2. Then this is in this situation, T-dependent case, this is a best possible irregularity improvement. But the situation is quite funny, very different from the case between 1 and 2. Also, this is a joint work with Professor Floridia. And namely, alpha order of the fractional derivative is between 1 and 2. But here, for the moment, although symmetry is not symmetry of the operator A is not seems not necessary, but so far only under symmetric elliptic operator. But we will consider, as I mentioned, that is our formulation. A is the initial, corresponds to initial displacement. B corresponds to the initial velocity. Then that case is rather strange. Namely, there exists countably infinite set, say lambda. Then lambda is an exceptional set for backward well-posedness. Then if T is not in lambda, we have always backward well-posedness, namely displacement at T, velocity component of capital T, H2 norm is equivalent L2 norm of initial status. That is very different situation. Also, lambda has accumulation points 0 and infinity. Therefore, for any small capital T, does not guarantee the well-posedness because of the 0 is accumulation points. Okay, now I must hurry up. Then within this framework, improved regularity can be done quite easily. Namely, taking time derivative, it is very common to improve the time regularity, especially for the wave equation and for the parabolic equation. Then what will happen for the fractional case? This is almost same. Just one example, alpha is between 0 and 1, then like that. Okay. Then basic result, F is in L2 in time t, then we can prove, say, this kind of regularity. But if we assume F is more regularity in time t, say H beta, but this is not very natural to take into consideration compatibility conditions at the t equals 0 between non-homogeneous term capital F and initial value. Our case, compatibility condition is represented F, not only F, but F minus AA. Small a is initial value. Small AA should be in H beta. Then we can naturally correspondingly lift up the regularity. Then if, by the way, if beta is greater than 1/2, this must vanish at t equals 0. Therefore, if beta is bigger than 1/2, actually this condition requires usual compatibility condition. That, okay. Then the proof is very simple because keeping the structure of the fractional derivatives, just operating a beta derivative, then after that we can apply basic theorem, say the third theorem. Then maybe I should hurry up a bit more. Then special case, if initial value is 0, we assume initial value is 0, and beta is same as alpha. Then this is a special case. A is like an elliptic operator, but double. Those are L2 regularity. And this kind of improved regularity usually in very convenient for many applications. Maybe, sorry, maybe I talked too slowly. Then one application.
I think you have, well, at least maybe 3 minutes now.
Okay, but I can stop here now. But okay, maybe the majority of this conference is also interested in inverse problems. Then I will skip it. Then to go to the final section. But that kind of improved regularity argument is rather simple than needed for some applications. Then finally, just to touch only the result, namely fractional transport equation. Namely, not elliptic, but the spatial part is first order. That part is a multiple derivative. Then that kind of equation was proposed by my engineering colleague related to geothermal energy plant, namely anomalous heat transfer under the ground with a lot of faults. In Japan, many volcanoes. Therefore, geothermal plant is very hopeful. Therefore, governing equation is used like that. Then, what is primary mathematical subject? Of course, unique existence. Then, maybe then at first the definition of the weak solution, but I think specialists can imagine what should be. And then after that, within this definition of the weak solution, one can prove the unique existence by the Galerkin method and the coercivity for the fractional derivative. That part is not so different, but of course, some small technical, non-trivial details. Anyway, in principle, that's all what I would like to talk. Then I'd like to stop here and thank you very, very much for your kind attention. Thank you very much.
Thank you very much, Professor Yamamoto. Now we can ask questions to Professor Yamamoto or comment his talk. Anybody interested?
Yes, I would like to ask a question.
Yeah, please.
I like very much your characterization of the, say, proper fractional derivative working on the Sobolev spaces and
It's sub-alpha.
Yes, but my question is, could you possibly extend this sort of results for LP, P different from 2?
Of course, that is very natural question, and this should be, but I have not yet.
Oh, I see.
Maybe I can make a comment.
Yeah, please.
So, so I looked at the case when P is not equal to 2 already in my PhD thesis. And so I have this characterization, but there I exclude the case where alpha is exactly 1 over P. So it's...
okay, yes.
But so you get Bessel potential spaces, H alpha P, and you also have to distinguish the case where alpha is bigger than 1 over P and alpha is less than 1 over P. And so when alpha is bigger than 1 over P, you have this extra condition that the initial trace has to be 0.
Yeah, on the other hand, just one question. On the other hand, in the case of P equal 2, 1 over 2 is an exceptional case, but it can be characterized by Lyon's interpolation. But
sure. So I just wanted to say that, so in my PhD thesis, I didn't look at this critical case, right?
Okay.
But it should be, I mean, it's also in a paper of mine from 2005 on maximal LP regularity for abstract Volterra equations.
Okay. Yeah, 1 over P is always troublesome.
And you also find something in the book of Jan Pruis. I mean, he already looked at the maximal LP regularity issue, and he used somehow also Michelin theorem, stuff like this. So this was just a comment.
Yeah, thank you very much. Thank you very much.
Thank you. Yes. Professor Zachar, you seemed like you wanted to say something more.
Yeah, maybe I can make some further comments. So,
Welcome.
so first of all, you also looked at the case when alpha is bigger than 1, right? I
Bigger
mean,
than one,
after your basic theorem, and so
Maybe formulation or
so do you have? But
formulation for PD or definition?
so concerning not the definition of the fractional derivative, but let's say the boundary value problem.
Okay.
Initial boundary value problem.
Maybe this
So
way.
yeah.
Yeah.
So you have a result on the solvability, let's say when alpha is in between 1 and 2, right? But you need more structure on your elliptic operator, symmetry. Is it?
No. Then to be precise, for general AT, T independent case, not yet.
You see, I think you might get a problem with well-posedness when you take alpha bigger than 2, let's say. So for alpha between 1 and 2, it's in some sense, it depends on your elliptic operator. If you take the Laplacian, right?
Yeah.
Then this is in some sense still a parabolic problem. It's a nice problem. Yeah.
Parabolic, but
parabolicity has to be understood in let's say in the sense of Volterra equations, where you look at the angles of your operators. So you have an elliptic operator if it is a nice operator like the Laplacian or negative Laplacian, the spectral angle is equal to 0. And then you can add a fractional derivative of order in between 1 and 2. And this operator has an angle.
but you are meaning T independent case. T independent case.
T independent case. Yes.
T independent case already solved about 6 years ago by means of the eigenfunction expansion. This is a very, very primitive way, namely
with eigenfunctions. Okay.
Yeah, that's all. But the main issue is that the T-dependent case.
Yeah, the T-dependent.
T-dependent case.
This should be difficult, I think.
Yeah. One needs a more difficult problem. But the T-independent case, the situation is special. Namely, one can use Mittag-Leffler functions. Also, the non-symmetric term does not matter because by means of something like a contraction mapping or perturbation. But the main issue is that the T-dependent case, namely careful execution of Galiokin's method.
Okay.
Yeah. But I can be for the moment optimistic.
Okay.
Of course, I'm not so sure.
Yeah, maybe things become better when you have more smoothness on your coefficients, but in the usual setting, when you have just bounded measurable coefficients, it should be very problematic when alpha is bigger than 1. But maybe you're right. In your case, things are better.
Especially for H2 regulating X. So far, I must assume extra T regularity for AOT. This is a bit unnatural. But anyway, minimum regularity, I'm not so sure of AOT.
Okay. And then maybe another comment. You also considered a fractional transport equation. Right? Okay. Yeah. And again, so I would expect that this equation behaves, it has better regularity properties in the sense that you should observe some regularization in contrast to the classical transport equation. So, do you observe such a behavior?
But the first category initial value is only.
Do you have some regularization? because it is in some sense also a parabolic equation, because the fractional derivative, it is an operator with an angle alpha times pi over 2, and then your transport term, it's like first order derivative, so it has angle pi over 2. Whenever you have the sum is less than pi, you can view it as a parabolic problem. This is the way I view it. And so, and you should have some smoothing. This is my question.
Yeah, but I'm not so sure. Even alpha equal 1, transport equation is...
No, alpha equal to 1 is, no, but you have, I'm speaking about alpha less than 1.
Mm-hmm.
So
alpha equal 1 is very different from other case.
Yeah, yeah. So I would expect to have some better behavior of the solutions in some sense.
Yeah.
I know that there are some results. Maybe I don't know if you know these papers by Kriepenberg and maybe also London on let's say Kriepenberg and London, who looked at also the non-linear transport equations, where instead of usual time derivative, you have a more general integral differential operator like a fractional derivative. But they also look at a more general class of kernels.
Griepenberg?
Griepenberg, yes.
Griepenberg, okay. Then maybe I can start.
And I think they have a notion, the notion of viscosity solutions, I think.
There are many works from the viewpoint of viscosity solutions.
Yeah.
Which I know. Also, Professor Giga has studied.
Yeah. Okay. Yeah. Thank you.
Yeah. Thank you very much. Anyway, I should compare with other papers. Yeah.
Okay.
Sabrina is raising her hand.
Okay, so please, Sabrina.
Hello, Professor. Nice to meet you. Thanks for your talk.
Thank you. You are any
my question is a little simple. In part 3, theorem 2, it would be useful to me to know in which way do you apply the fractional derivative to the series.
You mean the second theorem?
Yes, second theorem, part 3. That one.
Three.
Yes. Yes. No. Two. Oh, it's okay. That theorem.
Okay, 2. Yeah.
Yes. Sorry.
Yeah. Representation of the solution. Yeah.
In which way do you apply the fractional derivative to the series?
You mean applications?
No, mathematically, how you apply? Do you have any rule to interchange the series and the derivative?
Yeah, but that is the fractional time derivatives can be taken care perfectly only by the Mittag-Leffler function. Namely, for example, alpha derivative. Okay, for the moment we can consider Caputo derivative. Let us take formally Caputo derivative here. Then just minus lambda n times. Then minus lambda n times, then this is exactly the same as the heat equation, namely the Fourier solution. Then here is correspondent non-homogeneous term. A bit more complicated, but in principle the same. Taking Caputo derivative, here we can gain some minus lambda m. Everything depends essentially on the Mittag-Leffler function.
Yes, but my problem is before when you, how do you get to put the fractional derivative inside? Then when you apply it to the Mittag-Leffler, it's okay. But how do you apply it before? What do you do with the series? Yes, the justification. Any convergence in any space.
Oh yeah, but we know the asymptotic behavior of that. Therefore, this is roughly speaking, literal function is bounded by 1 over lambda n T alpha. Therefore, this is in principle parallelly to the case of the heat equation. One can justify the convergence, especially T positive.
I think you look at, I mean, you restrict to a time interval where you are away from 0, and then you can use the decay as a decay property of your Mittag-Leffler function to, I mean, you can use the lambda n in the
and
denominator.
If you can, if you can send the email address, I can send some related papers. But if you will see the argument is, I think simple. But if you are further interested in the details, gladly I will send some materials.
Yeah, thank you. I would appreciate it.
But anyway, I need your email address.
Okay, thank you.
Maybe I can make a comment because this is an interesting issue here. So we know that the Mittag-Leffler function has this, I mean, property that you only have this algebraic decay, and so you only get 1 over lambda n, right? Once. But this is in contrast to the heat equation, where in the heat equation case you would have an exponential function, and so you could add arbitrary many factors, lambda n, in front, and it's still bounded, provided t is bounded away from 0, right? And here it's only, you can only add 1 lambda n as a prefactor. And this shows that you can only gain 1 step in spatial regularity in the time fractional case, in contrast to the classical situation where you get, I mean, like C infinity. Yeah. It was just a comment.
Yeah, Professor Zakir's comment is almost equivalent to this kind of backward performance. Because not rapid decay, unlike exponential function. Therefore, we can estimate even initial value by some intermediate or positive time value, but by H2, thanks to lambda n. Or something like that. Anyway, please send your email address. Yeah, then I can send some files. Anyway.
Thank you. I see here that Piotr Mucha is shyly asking for permission to ask a question, so I would like.
As usual. As usual. So,
sorry, please try to be quieter a bit. Can you do something to be quieter?
Quieter? I'm too loud?
Yes.
Yeah, the volume is too big.
Now it's better?
Yes, now it's
better, but good.
Yes, now it's good.
Yes.
Now it's good, okay. So I have a question concerning the last part. So I mean this transport equation.
Transport, okay.
So my question is quite simple. If it is possible to solve Burger's type equation using this approach, using this fractional time derivative. If there is some problems or not?
Yeah, but the Burger's equation contains the second order EX?
No. Just implicit.
Okay.
Implicit Burger's equation, transport.
Of course, the main issue is that the nonlinearity. U times U sub X or something like that. The nonlinear term is U times U sub X.
Yes. Yes. That's simple.
This is not a simple question to me because
yes, because we do not have, because we cannot use method of characteristic. Yes.
Yeah, but also fractional transport equation rejects the characteristics. Of course.
Okay.
Therefore, one can do what one can do, but I think non-triviality may appear definitely, mainly coming from the nonlinear part.
Okay, so I mean this is not clear. Yeah.
So then it requires some work. We need a priori estimate guaranteeing the boundaries.
Yeah, this is the reason because I didn't see this.
And also, I did not touch anything about the nonlinear theory, but I am interested in the nonlinear theory. But at first, some preparation for the linear part is necessary. Therefore, maybe that is just be a very important future topics, I believe. And maybe some specialists are working for such kind of non-linear power equation, but maybe special case. For example, Professor Akagi from Tohoku University, but I don't know time fractional.
Okay, thank you.
Sorry, maybe I missed some differences. Yeah. Thank you.
Thank you. Any more comments or questions? Maybe our local collaborators of Professor Yamamoto would like to comment.
They must take care. They must take responsibility.
Yeah, but they vanished. They are not to be seen, and then they are very silent. So I don't know what to think of that.
Correct. I'm not always correct. I need a corrector.
I have a question. Professor Yamamoto.
Yeah. Hello. Yeah.
Alpha between 1 and 2, you show the equivalence of the data and some norm of solution, except some times. Yeah.
Yeah, sorry, I did not catch something like the microphone.
Okay.
Was not so.
Okay.
Yeah.
In the case of alpha between 1 and 2.
1 to 2, yeah.
Yeah, you show the equivalence of the norm of solution and initial data, and there are some exceptions.
Sorry, you mean that the fractional derivative or equations?
Yeah, this one.
This one. Okay.
Could you say something more why we obtain the set lambda?
Yeah.
What is the reason why the lambda appear here? And we have some
that is quite very simple reason, because at first we need a representation of the solution. Yes. Then the representation of the solution is written by Mittag-Leffler functions. But for that case, we need 3 kinds of Mittag-Leffler functions. And one of the main part E alpha 1, but alpha is between 1 and 2. But E alpha 1, some kind of Mittag-Leffler function can change the signs much more. Therefore, that case, 0 and 1, just we can take care that kind of coefficients. Okay, we can neglect that term, but the backward problem means that fix the capital T. We must solve a phi n, that is scalar product. But alpha is between 0 and 1. This Mittag-Leffler function is uniformly positive. But I did not write a representation formula for alpha between 1 and 2. But that part is more complicated than, roughly speaking, the determinant corresponding to the linear system of Fourier coefficients, 2 kinds of Fourier coefficients, A phi n and D phi n. Such determinant may be 0, must be 0 between 0 some capital T. That's why the existence of such exceptional sets exists. This is the main reason. But the proof, the reason is quite simple, just by the linear system and the determinant, and then roughly speaking, the determinant is positive, I remember, or positive or negative at capital T equals 0, but T infinity is a different sign. Therefore, some point at capital T, the determinant must be 0 by the mean value theorem. Sorry, intermediate value theorem and so on. But the proof is heavily depends on just the Mittag-Leffler function, because of this kind of eigenfunction expansion, the problem is reduced to just equating the Fourier coefficients with this kind of factor.
Okay.
And also for the ordinary differential equations, some result was available by Helm but he proves ordinary case. Yeah, but maybe it's very difficult to explain for satisfactory explanation. I hope, in a sense, some answer to your questions.
Yeah, thank you.
Okay, maybe now it's getting rather technical, so maybe this kind of discussion could be postponed to this one of breakout rooms that we can have. So I don't know, maybe we can accommodate one quick question or remark before officially closing this session, if anyone is interested. And if not, okay, then let's thank Professor Yamamoto again for his talk.
Thank you very much for your kind attention. Thank you very much. Thank you.
Thanks to all the speakers and participants of the morning session. Again, if anyone wants to continue the session. Sorry, Piotr, please, I will mute you if I can somehow, I don't know how. No, if anyone wants to continue discussing with Professor Yamamoto, I remind you about these breakout rooms. I don't know, is there Professor Rybka here? Piotr, are you here?
Yes. I'm
okay,
here.
so great. So one has to, in such a case, one has to address Piotr Rybka. And if not, then we see you, or at least, yeah, we see you at the evening session today at 5, right?
It starts at the same time as yesterday.
Yes, Polish time is 5. But, So see you and thanks again.
Thank you very much. Thank you very much. See you. Bye.
Bye-bye.
See you later.
Thank you for your talk.
Thank you. Thank you. Thank you so much.
Bye. Thank you very much.
Okay.
Bye.
Bye-bye.
マグニチュード八丈島東方沖マグニチュード 6.0 だと思う。
You reckon? So I must wish you all good night.
Yes, good night.
Because
thanks.
It's quite late and I have to make this one go to sleep.
Hi, Peter.
Okay, and you need to do it by example, I guess, by setting example, or if you are sitting here and having fun, then it's not fair.
That's right. I need to set a good example. Okay, yes, I must. So I will see. I'll talk to you all later.
Thank you.
Bye. Do we have to talk something about?
I don't know. I don't think so. I mean, we have Professor Giga here. I don't know if that's intentional by him or.
Hello.
Hello.
Thanks for your organization. I think we cannot attend the night session. Even
that's okay.
But I think I learned from our department yesterday that I think the visit to Japan is now possible, right?
It's now possible?
Yeah, now possible. Could you check? Relax. And now I think JSPS is allowed to come. So, it's quite recent. I just received this news Friday. Yeah.
Okay. Thank you very much. Unfortunately, I didn't get the certificate of eligibility yet. It did not arrive yet. So, I mean, I hope it will arrive in the beginning of next week. Your secretary wrote that the certificate was sent on Thursday last week, I think, or something like this. So